In this lecture video, we will be discussing the Sn2 reaction mechanism. So what is involved in the Sn2 reaction mechanism and all of the factors concerning the Sn2 reaction mechanism. First one, again, as a recall to all of you, that Sn2 reaction is the concerted process in which that we have the nucleophilic attack and the loss of the leaving group happens simultaneously. So in this reaction right here is the diagram showing the reaction mechanism that we have seen already. So in this case, this step right here is the nucleophilic attack. And this step here is the loss of the leaving group. And both of this step happen simultaneously. So in the transition state, what we will then see is that the bond is forming between the oxygen and this carbon. So in this case, this bond right here is forming. And the bond between the carbon and the leaving group is breaking. So as one bond forms, the other bond is breaking. And that's what we would see in the transition state, leading to the product over here. Now, so here are some of the experimental observations of this reaction. First one, let's focus on the kinetic of this reaction. What kind of observation when we analyze the kinetic of Sn2 reaction mechanism? Then first, here is the first observation. We find that the rate of this reaction is dependent on the concentration of both the substrate and the nucleophile. And more specifically, we have seen that doubling the concentration of the substrate. So here, let's say Rx refers to the substrate concentration. When we double the substrate concentration, we observe that the reaction rate doubles. So the rate doubles. And because doubling the concentration of the substrate leads to the doubling of the reaction rate, we will then see that the reaction is first order with respect to the concentration of the substrate. And another observation is that when we double the concentration of the nucleophile, we also observe that the rate of the reaction double as well. So here in this case, the reaction is also first order, is a first order reaction with respect to the concentration of the nucleophile. And combining both this together, the overall rate of this reaction equal to K multiplied by the concentration of the substrate raised to the first power, because it is first order with respect to the concentration of the substrate, multiplied by the concentration of the nucleophile raised to the first power as well. And overall, we will then see that the reaction is second order. So second order overall. That is the reason why that we call this an Sn2 reaction. The Sn2 here basically refers to the second order of reaction. Now here's another reason why we also call this Sn2 as well. So basically, when we analyze the mechanism of this reaction carefully, then the mechanism exhibits a step in which that the substrate and the nucleophile collide with each other. And because that's how we will form the transition state. And because this step right here involves two chemical entities, therefore it is said to be biomolecular, and therefore we call this Sn2. So the meaning to Sn2 is as follows. So Sn2. S here refers to substitution reaction. S for substitution, N is for nucleophilic. So nucleophilic substitution reaction. And number 2 here refers to biomolecular. So that's the meaning to an Sn2 reaction. But remember this, that Sn2 reaction happen in one step, where the nucleophilic attack and the loss of the leaving group happen simultaneously in one step. So remember that. Sn2, even though it has the number 2, it actually happened in one step. So Sn2 reaction happens in one step. And again, if we were to draw the potential energy diagram of this reaction, we would then see that here are the substrate and the nucleophile. And they would then interact with each other, and the bond between the nucleophile and this carbon is forming, and the bond between the carbon and the leaving group is breaking. So in this case right here, there's no intermediate. So here is our transition state. And the structure of the transition state, and there's no intermediate. Okay. Now let's investigate the structure of this effect of this substrate on the Sn2 reaction mechanism. So we discovered that the Sn2 reaction rate is sensitive to the structure of the starting alkyl halide. In this case, our substrate here is alkyl halide, and we use an alkyl halide as an example of a substrate. There can be other functional group that can also be served as the substrate as well. But here in this case, let's focus on alkyl halide as the substrate. And we discovered that the branching at the reactant carbon significantly reduce the rate of the Sn2 reaction mechanism. So here are the few types of alkyl halide right here. So we have a methyl halide, and we have a primary halide, and we have a secondary, and we have a tertiary halide. And in this case, all of them have the bromine at the leaving group. So when we use this as a substrate and measure the rate of the reactions, then we observe that in this case right here, then the methyl halide have the fastest rate of reaction. So this is slow. The tertiary alkyl halide is too slow to react. It do not undergo Sn2 reaction mechanism. And if we were to compare the ratio, so this is over 10,000, over 1,000 times, and this one is about 100 times, and then this one is about 1 time. So that their respective ratio in terms of reactivity. And the explanation for this is actually due to the steric hindrance of this different substrate right here. So in the case of a methyl halide, this have the least steric hindrance, and the steric hindrance is actually increasing as we go from the methyl halide into the tertiary alkyl halide. Now, how does this steric hindrance right here affect the rate of the reaction? Let's consider what is happening. So the steric hindrance make it more difficult for the nucleophile to come into attack. Because again, in the reaction mechanism, the nucleophile have to come in and attack this electrophilic carbon. So, and we can see here, if all of this substrate were to undergo the Sn2 reaction mechanism, we will find the following picture in this diagram. So here in this case, this is when we have the nucleophile attacking the tertiary substrate. And here the nucleophile attacking the secondary substrate and the primary. Now notice that how the nucleophile is very electron rich because it is rich in electron. In this case right here, we're not able to see the negative charge here, but then there is a negative charge on that oxygen. Now, regardless whether there is a negative charge on that oxygen or not, all nucleophiles by definition are rich in electron. So therefore, they will interact electrostatically, and we call this the steric hindrance when they come in to interact with the other methyl group. So a methyl group or any other alkyl group or atom for that matter are rich in electron. So if this were to come in and attack this carbon, it have to come in and repel and get repelled by this electron from this other group here surrounding this carbon. And the more of this that we have, then the more the steric hindrance will be, thus make it difficult for the nucleophile to come in and attack this carbon. So that's how steric hindrance can affect the rate of reaction. And in the case of a methyl halide, then there's very little steric hindrance at all. Therefore, it makes it very easy for the nucleophile to come in and attack this carbon. And as we have more alkyl group surrounding this reactant carbon, so we are referring to this carbon right here as the reactant carbon. In this case, this is the reactant carbon is called the alpha carbon. And the more substituted it is, the more difficult it is to react. So we would then see that a tertiary substrate does not get favored by the Sn2 reaction mechanism. It doesn't mean that it will not undergo substitution reaction. It simply does mean that it does not favor the Sn2 mechanism. And that would then mean that it may favor the other mechanism, which is the Sn1. So this is a great substrate favoring Sn1 reaction mechanism, but not the Sn2. And we will cover Sn1 reaction mechanism in a little bit. Now we also observe the following. The branching right next to the reactant carbon, which is the beta carbon, also have an effect on the rate of reaction as well, but it is not as significant as the substitution on the alpha carbon, which is the reactant carbon. So here in this case here, we also see here that so this is the beta carbon, and that is the beta carbon, and this is the alpha carbon, and the alpha carbon, and this is the beta carbon. Between these three beta carbon right here, the beta carbon in this example is have the most substitution on them. So it basically have a bigger electron cloud, and that can also have more steric hindrance with this nucleophile as well. So therefore, its rate of reaction is actually slower compared to this first example when we compare between these three. Now, so here is an exercise to make sure you understand this concept, so we can look at the structure of the substrate and be able to figure out how fast they will react in Sn2 reaction mechanism. So here are a few examples. Why don't you take a minute and think how we would rank this in order of decreasing Sn2 reactivity. So which one is most reactive? Okay, assume you have a minute to do this already. Let now go over this answer together. So how we would solve this problem is actually really easy. All we have to do is figure out what types of alkyl halide that we have. So here in this case right here, this is a primary alkyl halide. And again, this is primary because there's one other alkyl group connecting to this alpha carbon. And B is also a primary alkyl halide as well. And C is a tertiary alkyl halide. And then D is basically also a primary alkyl halide as well. So we have three primary alkyl halide, and we would know that they would be more reactive compared to the tertiary alkyl halide. And now, what are the differences between this A, B, and D? They are all primary, but then there's some differences among them. So here in this case right here, we will then see that B has a methyl group in here, and versus A have a methyl group in here. Now in A, the methyl group is basically at the beta position, versus in B, the methyl group is actually on the gamma position. And in D, there's no alkyl group at all. So therefore, we would then know that this would be least steric. The alpha carbon, this carbon here, in D is the least steric. So therefore, it will be the most reactive because it will be easy for the nucleophile to come in and attack this carbon right here due to the least amount of steric hindrance. Followed by B, because in case of B would then have the methyl group further away from this alpha carbon. So basically, this would be first, followed by B being the second most reactive, and then A, the third most reactive, and then C, the fourth. In this case right here, we would see that in fact, most the tertiary substrate will not undergo chemical reaction at all. So very, very slow, to the point that it will not undergo Sn2 mechanism at all. A very important topic regarding Sn2 reaction. And in fact, this is the reason that make Sn2 reaction mechanism very, very useful. So Sn2 reaction are stereospecific, meaning that we can use these types of reaction right here to produce a particular types of stereochemistry that we want. And we will not be making a racemic mixture. Therefore, it is valuable. And here is the observation right here. When X is bonded to a chiral center, so if the leaving group is bonded to a chiral center, then the Sn2 reaction mechanism produce only one enantiomer, and the configuration of the chiral center is inverted, meaning as follows. If we were to have a chiral substrate, let's say we have this substrate, let's say here is an ethyl group, and here is a hydrogen, and here is a methyl group, and Et for the ethyl group. So let's say this is the types of substrate that we have. So here in this case right here, the chiral center here is S. If we were to now take this substrate right here, where the alpha carbon is the chiral center. So again, this is the alpha carbon, and it is the chiral center. If we were to now take this and react this with SH, where this is the nucleophile, then we will then see that SH will be able to come in and react with this by acting as a nucleophile. And now the product that we would be seeing is as follows. The SH is actually attacking on this end right here, on this opposite end. So we'll come in, attack this carbon from this opposite end, and kick off this group. Yes, it is attacking from the back of this CBr bond right here. And that's the reason why that it is stereospecific. And we will then be producing this product. When this comes in to attack this carbon, it basically will push all of this group out a little bit, pointing to this side. And the hydrogen would now be still on the front and pushing on this side a little bit. The ethyl group would still be now, it push on the right side a little bit and it's still pointing down. And the methyl group is then pushed to the right a little bit and it is still on the back. And the bromine, the leaving group, is now broken up. And if we were to now determine this stereochemistry, this is now off. So what has this happened is that the chiral center, this carbon right here, in the course of the Sn2 reaction mechanism, its stereochemistry is inverted. And this inversion of configuration right here means that the nucleophile can only attack from the back side of where the leaving group would be, and never from the front side. So here is a diagram showing this reaction mechanism. So the nucleophile would actually come in and attack from the back. It never attacked from the front. If the nucleophile were to attack from this side right here, this would be called the front side attack. And in this case right here, in Sn2 reaction, we do not observe this to happen, but it will be attacking from the back. So again, this will be the reaction mechanism. And this is a very important part that we need to understand and be able to remember that Sn2 reaction are stereospecific. It will only produce one types of enantiomer, but not both of them. Has front side attack and back side attack both happen, then we will be making a racemic mixture. But that is not the observation that we have seen. So why backside attack? The explanation for this is actually quite simple. If we were to be looking at the potential energy diagram of the substrate, this is what we will find right here. So here in this case right here, this carbon, this side, this carbon right here is partially positive. So therefore, when the nucleophile come into attack, it will have to attack from the side that is positive over here, never from this end, because this part right here is rich in electron. And also we can also see that because this is rich in electron and a lone pair of electron on this leaving group right here, so there will be lone pair of electron in here that is rich in electron, and that is basically blocking the nucleophile from attacking in the front. So on conclusion, we can synthesize a specific enantiomer by using Sn2 reaction, and Sn2 reactions are stereospecific. And this is an important aspect that we need to remember, and this is what makes Sn2 reaction very valuable, because we are not producing a racemic mixture, but only one of the enantiomer. So now let's try some of this practice problem right here. Predict the product of this following reaction. So why don't you take a minute to work on this before we go over the answer together. Assuming you have a minute to go over this now, let's now go over the answer together. So here in this case, this is our substrate. And to help you guys with naming, let's try to name this molecule as well. So here in this case, what will be the stereochemistry of this group? So we can see the bromine is the group number 1, followed by the ethyl number 2, and this is number 3, and the hydrogen in the back already. So in this case right here, it would then be an R. So therefore, the name of this molecule is as follows, and we would name number this 1, 2, 3, 4. So let's write this 1, 2, 3, 4. In this case, 2R followed by 2 bromo butane. So that is our substrate. When we take this substrate right here and we react with hydroxide, then we will then see it will undergo Sn2 reaction. And here in this case, the nucleophile will be come in, and again, it have to attack from the back side of where the leaving group will be. Here in this case right here, the leaving group E basically pointing out. So the hydroxy group actually have to attack from the back side and kick that off. So therefore, when we produce the product, then the product would now be pointed in the back, keeping everything the same. Now the nucleophile will be added to the back, and we have our hydroxy group over here. And our bromine will be broken up to become the bromine. So that would be the product. Now, so it depends on what the rest of the group would have in here. That what dictates stereochemistry on the product. And so in this case right here, we would then see the inversion of configuration. However, what is the stereochemistry of this? This because we know this is inverted, it does not mean that it will be S automatically, but we have to still determine its configuration. A lot of time, because the nucleophile that is being added, in terms of ranking in priority, when we determine the stereochemistry, it is normally the group number 1. And because this is now swapped, so this is why that R become S and S become R. But the exact configurations is something that we still have to use the guideline how to determine the stereochemistry. So here in this case, this will be number 1, number 2, number 3, and it will be R going to the right, but because the hydrogen point to us, so we have the opposite. So in this case, the name of this molecule will then be 2S and butane 2R. That's the name of this molecule of the product. Let's now try another example. So here in this case right here, we have this substrate and reacting with excess amount of sodium cyanide. Now in sodium cyanide, again, this is an ionic compound with some sodium positive, and the carbon on the nitrile, that is negative right there. So basically, this is our nucleophile. The carbon is negative, and it's the carbon that carry the lone pair of electron, and that is our nucleophile. So if we were to have excess amount of this, how would this come in to react with our substrate? Well, in this case right here, there's up to 2 different types of alkyl halide. We have a bromine right here, and we have a chlorine right here. And both of this are leaving group. So here in this case, we can see that if we would have excess amount of this, the cyanide can come in and attack this from this back side. Kick this off. And if we were to have excess of it, all the excess amount can come in and attack this carbon right here from the back side of this CBr bond as well. So we'll be producing this product. Now the cyanide would then be on this side, and the hydrogen is now on the other side. And same thing, another cyanide is added right here. And that would be the product. And if we were to determine the stereochemistry, this is S, and this one is R, and on the product, this is now become R, and this one right here is then S. So the stereochemistry is inverted. Now moving on to the other effects, the other factor of Sn2 reaction. So here in this case, let's now analyze the effect of the leaving group. Because the leaving groups, the types of leaving group can also favor or disfavor Sn2 reaction as well. So here, the leaving group can also greatly affect the Sn2 reaction rate. So now here is some of the observation right here. We will be taking a nucleophile, and all of them are hydroxide, and the substrate. These are the different substrate with different alkyl halide on them. And we are performing this experiment right here and measuring the rate of reaction so we can see what will be the effect of the substrate. In this case, they have different leaving group on them, on how does that affect the rate of the reaction. So the products, this will be the products of all of this reaction. And now when we analyze the rate of this reaction and we compare the rate, relatively, these are the ratio right here. 1 to 200 to 10,000 and to 30,000. So it turned out that the iodine, this type of iodine as the leaving group, has the fastest rate of reaction. And fluorine have the slowest rate of reaction. So why? So it's very important that we understand this why right here. Now, so it turned out as follows. The bond strength between the alpha carbon and the leaving group matter. The reason is because when we analyze the reaction mechanism, this bond right here is the nucleophilic attack. So that's one of the steps that can affect the rate of the reaction, followed by the loss of the leaving group, where this bond right here is broken. The bond between this alpha carbon and the leaving group is broken. So that is part of the reaction mechanism. Now, depending on this bond strength of this carbon and leaving group bond right here, the strength of this bond right here affects the rate of the reaction. We can imagine that the stronger this bond, the less likely it will break. And the less likely it will break, the slower the rate of the reaction would be. So that's how this leaving group can affect the rate of the reaction. So we can see the stronger this bond equal to the slower the reaction. And we have seen previously already, these are some of the bond strength right here. When we look at the bond strength between the carbon to this different halogen right here, these are the bond length and the bond strength right here. So we will then see the bond between carbon and iodine is the weakest bond. And the weaker it is, the more likely it can break. And you can also see here the reason why this is a weak bond is because of the longer bond length. So the longer the bond length, the weaker the bond. The weaker the bond, the more easily it can break. And the easily it can break, the faster the rate of the reaction would be. So that is how the leaving group can affect the rate of the reaction. And now, let's analyze this next effect right here. The effect of the nucleophile on the Sn2 reaction. So in the Sn2 reaction, the nucleophile attack and the loss of the leaving group happen both simultaneously. So therefore, one can imagine that the better of the nucleophile that we have, then the faster the rate of the attack, nucleophile attack would be. And therefore, the faster the Sn2 reactions, right? Now, so by definition, anything that is rich in electron would like to donate electron. And as it donates electron, it can be served as a base or a nucleophile, depending on what is given the electron to. So strong bases are strong nucleophile, but not all strong nucleophile are basic. Because basicity is being defined by the equilibrium constant for abstracting a proton. So here in this case right here, if our nucleophile were to donate electron to a proton, it is served as a base, and therefore basicity. Versus the nucleophilicity is when this nucleophile right here is now given electron to this carbon right here, but not the hydrogen, and kicking off this group right here. So that is called nucleophilicity, because the base or the reagent in this case right here is acting as a nucleophile. The stronger the nucleophile, the faster the rate of the reaction. Now again, strong bases are strong nucleophile, but not all strong nucleophile are basic. Because some strong nucleophile, they would only strictly behave as strong nucleophile, and they are not basic. And again, to figure out why they are not basic, then we would then basically looking at the corresponding pKa of a conjugate acid. And if that is a low pKa, then we would then know that it is not a strong base. And that's what makes that nucleophile not a good base. So here is how some of the nucleophiles are ranked right here. So here in this case, these are some of the functional group. And this kind of functional group right here are called weak nucleophile. Versus these are the moderate nucleophile right here. And these are some of the strongest nucleophile. Now, what makes them a stronger nucleophile than the other? Well, the answer, in order for them to be good nucleophile, they has to have electron rich and willing to donate the electron. And therefore, if we were to be ranking all of this, we would then see that when a nitrogen is negative, meaning it is rich in electron, and due to the low electronegativity of nitrogen, meaning it will be very willing to donate the electron. Thus, it is strong nucleophile. Now here in this case right here, iodine is a strong nucleophile, but it is not a strong base. So that goes back to the statement that we have seen previously as well. So iodine is rich in electron, therefore making it a strong nucleophile. However, it is not a strong base, because if it is behaving as a base, and it would then pick up a proton, and the pKa of the corresponding Hi again is low. This is about -8 to -9. So therefore, it will form a very strong acid. And we know that forming a strong acid is not favorable, because it will happen the other way around. So therefore, iodine is a strong nucleophile, but not a strong base. And also, SH and SR, this is also strong nucleophile as well. And the reason why here in this case is because, again, the sulfur is negatively charged, so therefore it's rich in electron. And we also know that sulfur have low electronegativity as well. So therefore it is willing to donate electron, making it strong nucleophile. So a lot of species or reagent that have negative charge on them tend to be strong nucleophile. And again, the best way to see this is to ask ourselves this question: how rich in electron is it? And second, how willing is it in giving the electron away? So how rich, how electron rich is the reagent. If we were to have something that is negative, if there's something that have a negative charge on it, it would be more nucleophilic compared to when it's simply just a lone pair of electron. And second, how willing is this reagent right here in donating electron? And that when we be using electronegativity. The lower the electronegativity of the atoms that make up the nucleophile, then the more willing it is in giving electron away, therefore becoming the better nucleophile. So low electronegativity equal better nucleophile. And next here we have this in the middle that are considered to be moderate nucleophile. And the reason why is because they are all neutral. Now, why is iodine over here a strong nucleophile versus bromide over here is a moderate nucleophile, and why chloride here is a moderate nucleophile as well? So what makes iodine? So we can see here that iodine is a stronger nucleophile compared to the bromide and the chloride. So why did this happen? We will see the explanation in a little bit, but it has to do with the size. Size does matter. Now, so here are some of the trends in nucleophilicity, or the strength of the nucleophile. So first, we see that a negative charge nucleophile is stronger than its neutral counterpart. So in this case right here, let's say we're gonna write a few examples. Let's say here would be the stronger, better nucleophile, and this is poor nucleophile or poorer nucleophile. So we will then see that hydroxide is a better nucleophile than water, it counterpart that is neutral. And we also see that then methoxide will be a better nucleophile than its counterpart that is neutral, which is basically methanol. And H2 negative will then be a better nucleophile than its neutral counterpart with the NH3 ammonia. So basically, these are more electron rich, therefore equal to better nucleophile. Thus, it's very important that we determine the formal charges of our reagent, so we know whether something is negative or not, because that sign, that formal charge, tells us how rich something is in terms of its electron. Now, so here is the second trend in reactivity as a nucleophile. So the nucleophilicity decreased from left to right across the periodic table. Here is what we observe right here. Methyl anion is actually a better nucleophile than NH2, and NH2 is more reactive than OH as the nucleophile, and this is more reactive than fluoride. So among all of these substances right here that are negative, carbon, when a carbon is negative, we will have a carbon ion, and that is more reactive than a fluoride anion. And the reason is, again, it has to do with electronegativity. So this would be the better nucleophile. And the reason why is because this is less stable. If the carbon were to have the electron, it is less stable because the carbon have low electronegativity. It does not want to become negative, therefore more willing to donate the electron. and acting as a stronger nucleophile. Versus over here, then we would then see that if the electron were to be on a fluoride, the electron would then be more stable. And then more stable because it is more electronegative compared to a carbon that is negative. And if it is stable with electron, that means it is less willing to give the electron. And therefore would not be a good nucleophile. Now, so the third factor, the size, as I mentioned earlier, the size of the nucleophile also have a tremendous effect on the ability, on the strength of the nucleophile as well. So here in this case right here, let's investigate this. So we observe that the nucleophilicity increase down the periodic table as the size and the polarability increases. And this polarability right here refers to how loosely the electron are held. And the more loosely the electron are held, then the easier it can move to a positive charge. So let's discuss this in a little bit. So here in this case right here, we have observed earlier already that iodine is actually a stronger nucleophile compared to bromide. This is a strong nucleophile versus bromide is a better nucleophile than the chloride, and the chloride is a better nucleophile than the iodine. So this is the weakest nucleophile, a poor nucleophile, versus this a moderate nucleophile. So why is this the case? Then the answer, because of size. So here is what happened right here. The bigger atom, then it has softer electron shell, meaning the electrons are well dispersed throughout the whole atom. And it can stop overlapping with the reactant carbon from a further distance. Because its orbital is now bigger, therefore it can form the bond to the carbon at a longer distance. And through a long distance, the bond can form better. And that's why it can attack the carbon better. So here in this case right here, if we were to be looking at orbital, here is the fluoride and here is the iodine, and the sizes of the fluoride and the iodine. So here in this case, we would then say the fluoride to have a hard electron, meaning all of the electron density in here are very dense. And because it's very dense, it's not as soft. Versus here with the iodine, because of its bigger orbital, it is then said to have a softer shell of electron. And as it comes in to react with the substrate and forming a bond, because all of this would then be donating electron to this orbital. Now, so this is basically, this orbital right here is then called the anti-bonding orbital. So as the nucleophile come into attack, it actually donates electron into this anti-bonding orbital. And as this electron is donated into this anti-bonding orbital, it weakens this bonding orbital right here, making this bond become weaker. So the more electron we have in the anti-bonding orbital, the less electron we will have in the bonding orbital in here, therefore making this bond weaker. And as this it becoming stronger, this become weaker. As this bond is formed, this bond is broken. So that's what happened in the transition state. Now, if we were to now compare the differences between the two transition states when we have fluoride coming to attack the substrate versus iodine attacking the substrate, because the shell of iodine is bigger and it is easier to polarize. Therefore, it can actually donate electron over a distance. So distance here is further, versus here is shorter, thus making this bond become easier to form. And because this become easier to form, that would make this a strong nucleophile, because it can form longer over a greater distance. So there's more bonding in here compared to this one, we have less bonding. So that's how size can actually affect the strength of a nucleophile. The bigger the size of the nucleophile, then the more easy it is in forming a bond with our reactant carbon, therefore making it a better nucleophile. And if we were to also go back and compare, we will then see that SH negative is a more stronger nucleophile than hydroxide. And again, because sulfur is bigger compared to oxygen. They are both in group 16, but because sulfur is bigger, therefore it's more reactive. And the other explanation, it also have to do with electronegativity as well. Sulfur, not only that it is bigger, but it's less electronegative, meaning it also more willing to donate the electron as well. And that's something that we can also find in all of this example with our halide. And similarly, we will then see that pH2 will then be a better nucleophile than NH2. And again, this is because of the size of the phosphate.